This is the way we usually arrive at the inverse square law of gravitation. You assume that the planets move around in circles with the sun at the center. Then you use Newton's law of motion, F equals ma. Next, you use one of Kepler's laws, the one that says that the period square is proportional to the radius cubed. Then, with a little simple algebra, you soon arrive at the relation that the force is inversely proportional to the square of the distance. Now, you and I know that all Earth satellites actually move in elliptical paths, and so do the planets. Today, we can get quickly the kind of data that Kepler got so painstakingly from Tycho's observations. In both cases, the story is the same. The planets or the Earth satellites move in elliptical paths. So it should be possible to arrive at the inverse square law from an ellipse. Now suppose we consider an Earth satellite moving in an elliptical path. Incidentally, Kepler was the first to realize that the planets move in elliptical paths with the sun at one focus. In this case, here, the Earth satellite moves in an elliptical path with the Earth at one focus. This is the logic I propose to follow. Once again, I will use F equals ma. This time, with special emphasis on the fact that both the force and the acceleration are vectors. Now, instead of using this, I will use another of Kepler's laws, the one that says that the radius vector sweeps out equal areas in equal times. This law, like all three of Kepler's laws, is based on direct observation of the planets. But today we get the relationship from observation of the satellites. It holds for Earth satellites and planets. Now we want to show how the inverse square law follows from this sequence of thoughts. Now, there is a basic difference between these two cases. A circle has a fixed radius, and so we have to go to different planets in order to sample the gravitational pull at different distances. On the other hand, within a single ellipse, the radius vector keeps changing in size, sampling, so to speak, the gravitational pull at different distances, even within one revolution. Well, this is what we have to do. Here's a satellite moving in an orbit. The Earth is here. We want to sample the gravitational force on the satellite here, here, and here. Now, one way to measure forces is to reason back from accelerations. If I can figure out how much the satellite will accelerate in a given time when it starts here, and how much it will accelerate in the same time when it starts here or here, I'll have a way of comparing forces. Now, in order to do that, I need a way of comparing times. I want to be sure that the time interval remains the same in all three cases. Well, I have a way of measuring time intervals. Kepler's second law. Equal areas in equal times. If I can move this area from here over to here, then the time required for the satellite to move this distance will be the same as this time, or this. Now, obviously, I'll need a more accurate ellipse if I'm going to get significant measurements from it. Well, that's exactly what we'll do. I will use Kepler's second law to be sure my time intervals are right. And then we'll see whether or not we can arrive at an inverse square law of gravitation. By using a carefully drawn ellipse, by analyzing the motion of a single Earth satellite, or any other body moving under the action of a central gravitational pull, as it moves in an elliptical path. Here's an ellipse. Now pretend the Earth is out of focus here. And imagine the Earth satellite moving around in an orbit like this. Now what I want to do is to sample the Earth's gravitational pull at 3 different places. Here, here, and here. And this is the way we'll do it. I will choose an arbitrary point on the ellipse at a distance r. I have that distance already notched on my ruler. And then at a distance 2r, where I have another notch. And a third notch at 3r. Like that. Now, if it weren't for the pull of gravity, the satellite would want to fly off along a tangent, like that. One way to draw a tangent line is to use the focal property of the ellipse. I can get my 2 radius vectors by using a string. When the mirror is tangent to the ellipse, the reflection of one radius vector looks like an extension of the other. So, if there were no gravity, the satellite would want to fly off along this line. Now my proof requires 2 other tangent lines. One at 2r. Where I repeat the process. There's my second tangent line. And the last one at 3r. And there I have my 3 tangent lines. Now remember, if there were no gravity, the satellite would go that way, or that way, or that way. It's the pull of gravity that keeps the satellite in its orbit. But at this point, it is 3 times as far from the Earth as it was here. So the pull of gravity is weaker. How much weaker? That's what we want to find out. Well, suppose the satellite moved from here to here in an arbitrary time. Let's call that time t. The radius vector would sweep out a corresponding area. This area. The radius vector would move from here to here, sweeping out this area. Now take a look at this vector. The one that goes along the tangent line represents the distance the satellite would move in the arbitrary time t if there were no gravity. And this little vector, pointing along the radius towards the center of the Earth, is the distance that the satellite would fall towards the Earth in the same interval of time t. Now consider this point. How far would the satellite move in the same interval of time t, starting from here? Well, this is where I need the law of areas. I need some way of transferring this area over to here. I can do it this way. I've put just enough pellets in the beaker to fill the area. Now, it's quite obvious that if the pellets don't climb on top of one another, I have a quick way here of filling an area. I'll put a mark here at the end of this radial line. Now, if I don't lose any pellets or gain any, I can transfer this whole total area to this region. In order to do so, I have to open up my arc. It's not as easy as it looks. Obviously, this isn't the first time I've done it. Once again, I'll put a pencil mark at the end of this radial line. Now I'll move over to the third area. This time I have to open up the arc quite a bit. There. There's my third radial line. And now I have the marks I want, so I can get rid of my pellets. Now remember the meaning of this vector, the one along the tangent line here. This is the distance a satellite would travel in a time t if there were no gravity acting. And this is the distance the satellite would fall towards the center of the Earth in the same time t. This is velocity times time. But because this is the third tangent, I will call this v sub 3. And this is 1/2 at squared. Similarly, I will call this a sub 3. Using similar notation, this vector is v sub 2t. And this vector is 1/2 a sub 2 t squared. This vector is longer than the other acceleration vector. Now moving over into this position, it's apparent that this vector is much larger than the acceleration vectors we have seen. I will call this 1/2 a sub 1 t squared. And the one along the tangent, v sub 1 t. Now I have three acceleration vectors, and I'm in a position to answer the question, how much is the acceleration changing? I can make the comparison this way. This acceleration vector is this long, and it fits into this one 1, 2, 3, 4 times. So this acceleration is 4 times larger than this one. I'll call this one 1, and this one 1/4. Once again, let me measure this acceleration vector. And see how it fits into the original one. 1, 2, 3, 4, 5, 6, 7, 8, 9 times. This vector is 9 times as large as this one. So I'll mark this one 1/9. Well, that does it. When I doubled the distance, the acceleration became 1/4 of the original value. When I tripled the distance, the acceleration became 1/9 of its original value. Now, since force is directly proportional to acceleration, everything that I've said about acceleration holds true for force. And that makes an inverse square law of force seem very plausible. Now, I used 1, 2, and 3R, but I might have used a value like 2.65R. I assure you, the inverse square law would hold there, too. Now, I hope you understand what I've done and why I've done it. You might object that this is an approximate method only. This is true, but the approximations get better and better as the areas get smaller and smaller. In any graphical proof of this type, you have to make a compromise. You have to make the areas large enough so you can see them, and you have to make it small enough so that the radius vector does not change very much in direction or in magnitude. Well, you might wonder why I tried a proof of this sort instead of this. For years, the books have used this law and circular orbits to arrive at the inverse square law. But today, everybody knows that Earth satellites move in elliptical orbits. Of course, the planets also move in elliptical orbits, but they are so nearly circular that you can get by with this sort of a proof, and there's nothing wrong with it as far as it goes. But I wanted a proof that started off with an elliptical path. Now, make no mistake about it. If you repeat this construction and understand the significance of every step that you take, you will really understand the inverse square law and the motion of satellites.